Okay, so now we are going to switch to MATLAB to try to first implement a simple softmax regression using neural networks and then add additional layers to make things better. Okay, so that's a plan. I just want to keep this on the side to make correspondences. Okay, so here we go. This is the program that does this neural network training. And we're still going to use MNIST as a example data set. Obviously, you can generalize it to other kinds of data sets. Spelling mistake. Okay, so we're going to clear all, close all CLC, load MNIST, and then just going to measure the size of the data set. So number of pixels is the second element of the size of train X. So of course that's 784, which is going to be the number of inputs that we have. And then how big is the training set? It's going to be length of train Y. How big is the test? That's 60,000, I think. Test data is about 10,000. So it's just measuring the usual sizes of various matrices. And here is something funny, perhaps. So MATLAB's deep learning toolbox, I guess, has a variety of input layers. So MATLAB deep learning input layers. So it's got a variety of input layers. One is called an image input layer, which is for a 2D image, apparently. Another is called image 3D input layer, which is for 3D images, and sequence input layer, feature, ROI. These are all different kinds of input layers. This is with the so-called deep learning toolbox. There's also a different sort of neural network paradigm which allows you to have other kinds of inputs, just numbers. But here, at least if you're going to use this particular deep learning toolbox, we're implicitly using one of these input layers. So it turns out that if we, I'm going to explain this in a minute, but before I explain that, I'm just going to explain this cell or this section, okay? So this section corresponds to basically the structure of this neural network. We're just defining what the layers are in the neural network. So you have the first layer, this one, which is the input layer. In this case, it's an image, MNIST, right? So we use the so-called image input layer, okay? And we'll talk about the size in a minute, and that has to do with this section. This is basically the size of each input, okay? And then we have a fully connected layer with 10 neurons. Okay, so that's these 10 neurons here. It's the fully connected layer. MATLAB actually allows us to have, when it actually has a layer of neurons, it actually does not have the activation function, actually. So when you say fully connected layer, it actually just means the linear transformation between Z's and the Q's, okay? So that's actually just a linear transformation that takes images, and once you pass through this layer, you get a linear transform version of the image. That's Z, and then the Z's go to the softmax layer, so softmax layer, and then the last layer is not really a layer of the neural network, but it's a layer that we need to have to be able to train the neural network, which is basically this loss function, right? So the outputs from the neural network itself P, the probabilities, are passed on to the loss function to actually minimize it. The so-called classification layer basically computes the logistic loss function, or it's also called the cross entropy loss function, whatever, variety of names. So that's what's the last layer is, and it uses the data and the output to try to minimize the loss function. Okay. Okay, so those are the layers. The only thing that we need to make sure is that the image input layer has the appropriate shape and size that corresponds to the kinds of inputs that this thing allows. Okay, so MATLAB expects for a 2D image, MATLAB expects the following thing. So each image, a 2D image, which is just an image, right, is RGB, red, blue, green, right? Because of that, it's actually a three-dimensional matrix, right? So if you have a matrix that is, let's say, I'm just going to make a matrix of zeros here, but so this matrix 100 by 100 by 3 can be interpreted by MATLAB as a 100 pixel by 100 pixel image, and with 3 channels, red, blue, green. Okay, so this is the format of images in MATLAB. RGB format, as we think we've already seen for that one of the this is a standard format. Because here everything is 0, if you just go I am show, okay, it just looks like a black box because all the colors are 0. And then if you go it's a white box. And actually we can try red, blue, and green and so on just for fun. A of let's make everything zeros again, and let's say A of all of the first dimension, all of the second dimension, and then just the first whatever slice of the third dimension. If you set that all equal to 1, because it's RGB, what we have set is the first slice, we've set them all equal to 1, all of the slices is 0. So we're going to get, I am sure of A, we should get just a red image. Okay, so let me just close all, just a red image. And if I set the second channel to 1 as well, both red and blue or red and green or 1. If you combine red and green, apparently you get yellow in this world, RGB. And then if you just have the second slice equal to 1 in the first slice, you just get green because you just have green on, etc. Right? You can get gray by having A equals 1s, and then we can just say 0.5 or something. All the elements are 0.5. It's some grayish color. Okay. Anyway, so that's what images look like. That's darker shade of gray, lighter shade of gray, etc. Okay, so that's what image looks like. This is a 100 by 100 pixels thing. Okay, that's RGB image. Now, this image input layer, each image is now going to be RGB. So it's number of pixels width, number of pixels height times 3. And then we are actually passing all the input that we have. So it's basically 60,000, right? So we're basically constructing a matrix here that consists of um, width of pixels, height of pixels, uh, one, because we are only, this is not color, this is black and white, uh, and this is 60,000. And here, what I could have done is used square root of 784, which is 28. So ideally, I could have said 28 by 28, in which case, what I needed to do is actually reshape the input into 28 by 28. But what we are doing is just retaining, because the MNIST is just rows, like each image is a row. We're just retaining that. So it's kind of this weird image, which is like 784 pixels long and just 1 pixel high. So we are trying to interpret images of that flavor, 788 pixels long and 1 pixel high, because we are too lazy to reshape it into 28 by 28. So this is the size of the image, and this is the number of channels. Instead of 3, we just have 1 because we're just using black and white or grayscale. And this is the number of data points that we have, 60,000. Okay, and MATLAB wants us to. So this is what I call a 4D matrix. Each image is already a 3D matrix. This is a 4D matrix, and MATLAB wants 4D matrices as inputs to the image input layer. And I suppose this is the um, uh, format that it wants, I suppose, okay? Where this is the number of pixels and this is the training data. So if you looked at train X, which is num train data times num pixel size, that gets stuck into the train X4D in this manner, okay? And train Y is just our usual 0, 1, 2, 3 until 9. Those are just regular numbers, or they may be integers or something. But what we are doing here is converting them into, telling MATLAB that it's a categorical variable. You should not treat these things as numbers, but you should treat them as categories. Okay, so they're conceptually different. So doing that here. That's for the training set, where we first, the images we arrange into a 4D matrix. The outputs we arrange into a categorical array, which is a column array. And then we do the same for testing, okay? We've already defined what the layers of the neural network are, and I have commented out a whole bunch of other things. Here, we provide the options for the optimization. So MATLAB comes with its own little optimization procedure just for deep learning or neural network learning. We're not using fmin-unc or our own stochastic gradient descent. We're going to basically use this function called train network, which has within it some kind of stochastic gradient descent, multiple versions of stochastic gradient descent, which we can call, okay? So that's what we're going to do. We're going to basically train the network with all the data. This is the input. This is the output. The layers we've defined here. And options. Options are how to train the network. These are the training options that have been defined. SGDM is the stochastic gradient descent method. M stands for, I think, a version with momentum, which is a variant of stochastic gradient descent, which I'll briefly talk about at some point. But suffice it to say that it's a small variant of the stochastic gradient descent algorithm. Pretty simple. And then learning rate, which is alpha, which we just picked something. Mini batch size, we say how big is a mini batch, 128, maybe 100, I don't know. It's nice to make this mini batch size a, a factor, an exact factor of the full data set. So if you have 100 and if you have 60,000 images, then 60,000 by 100 would be 6,000. So each epoch will be, um, it'll take like 60 iterations or 60 iterations. 60,000 by 100 would be 600, I guess, 600 iterations per epoch. And then we do 20 epochs, which means 60,000 divided by 100. This is one epoch has 600, and then 600 times 20. So we are saying, let's do 12,000 iterations is what we are saying. Or 20 times 20 complete passes through all the data is what we are saying here. This is an option so for each epoch, we can use the same set of mini batches. So the first mini batch is the same in each epoch, or we can sort of shuffle around the mini batches so that the order in which you see the data is different on each epoch. So you can do that shuffling. We provide the validation data or the test data here, which is here, which we can provide here, which we just say is the test set. Validation frequency. Now you will see in the when we run this thing, you will see that it's trying to decrease the training error. In other words, it's trying to minimize the loss function on the training set, which is a 60,000 large set. But recall that what we want to do is decrease the training error, but make sure that the test error doesn't go too high, because if the training error is driven to 0, you may be overfitting potentially. This is an interesting topic which we will cover later in more detail. But we always want to keep track of the test error as well, test or validation error, to make sure that it doesn't grow too large as well. We want roughly the training error and the test error to be roughly similar. So in any case, we want to check. So what this procedure allows is to check the test error every 30 so iterations or something like that. We can make it 50 or something like that. Doesn't matter. So you'll see the plot of that, how the test error changes or the validation error changes, as well as how the training error changes. Verbose equals true just means that it will give you a lot of information on the screen as it's proceeding with the optimization. And then it will also provide plots. And the plot that we're requesting is the progress in the training. In other words, how well the function approximation is doing. Okay, so that's basically it. I'm going to comment these things out for now and run this thing piece by piece. So clear all cores of CLC, load MNIST data, just figure out the size of the data set, rearrange the data set in a manner that MATLAB's deep learning toolbox likes. That's this block. Basically convert all the images, all the images into 4D data, and all the outputs into categorical variables. Okay, that's what this thing is. And then define what layers we're going to have in the neural network. Run it. Takes a couple of seconds. Define the options for the optimization algorithm. And then finally run the train network thing. And it's busy a little bit. Let's see. A window will pop up in a second. So notice that it's saying training on a single CPU. So all we have is this computer, so it's just training on that. We will change this in the next lecture or two so that we can train on GPUs, which might make things faster. Okay. Okay, so um, notice that, okay, it started with very low accuracy, I don't know, 5% accuracy or something, and then incredibly quickly, using stochastic gradient descent, went up to some 87-ish percent or something like that. Okay, and then now it's just bouncing around. Um, it's completed epoch number one. That's 600 iterations, as you can see. So over 600 iterations, it's seen all the data. Epoch number two, epoch number three, etc. I should probably not have asked for 20 epochs because it looks like it's already achieved more or less steady state. It's just bouncing around at this 87-ish percent. So what I'm going to do is try to see if I can stop it. Okay, I stopped it rather than let it go to all 20 iterations because it didn't look like we were making that much progress. Um, when it actually stopped, the validation accuracy is 89.35%, almost 90%, and took about, I don't know, I guess it got up to there maybe pretty early. Um, yeah, pretty good. We can test the prediction accuracy here by rerunning it. Um, if if so, of course, it's maybe I closed that thing, but if you actually saw the plots that it was giving, it was showing two different curves. One of them was how the training error changes, and the other one was how the test error changes. Let me actually run this again to show that. So this dotted line um, with the black dotted line that just is evaluated every 50 iterations, here, 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 here. That's actually testing on the validation set. The light blue that you can see that sort of is going in high frequency, that's actually the training error or the training accuracy on every gradient descent iteration. How much is the training error or how much is the training accuracy on the training set? That jumps around a lot because it's stochastic gradient descent. Because of that, there's a stochastic aspect to it, and the current performance will depend on the current mini batch that we picked. And then there is a darker blue line that is overlaid on the more um, bouncy thing. Darker blue line is a smooth version of the more noisy thing. The smooth version is already a bit noisy, but hey, that's the nature of the algorithm, I guess. Anyway, so those are those things. And then this is the actual loss function that is being minimized, which is the logistic loss function or the cross entropy loss function for classification. And it started somewhere at 15 and then it went down pretty quickly. Kind of similar to what happened when we implemented stochastic gradient descent on our own, right? Um, it went down pretty fast. Okay, so I'm going to stop that again. So this black dotted line, which is evaluated once 50 iterations, um, it's good that it's mostly tracking the training error or training accuracy. The test accuracy or the validation accuracy, which is basically your training on the training set, and then testing on the test set or the validation set. If the two accuracies are similar, that means that you're not necessarily overfitting much. If the training accuracy is high, but the validation or test accuracy is very low, then that means that you're overfitting to the training set. In this case, it doesn't look like you're overfitting to the training set, at least as uh, decided by this validation or test set. Okay. Okay, so I'm just going to close that. So we got up to about 89 point or 88 or 89% accuracy, not too bad. Um, that's with just regular logistic regression because we don't really have the layers here, don't have ReLU or any of the activation functions and so on. Um, so it's just implementing this stuff, right, which is the exact same thing as logistic regression, multi-class logistic regression. Um, what we're now going to do is add a couple of more layers between the image input layer and the softmax layer. And we will see immediately that the accuracy increases. Okay, not quite immediately. So that's this part. So MATLAB allows you to add these layers very simply and easily. So instead of image and then fully connected in softmax, we have image, fully connected softmax here, but in between we added a fully connected layer. So basically these QN going up to 100 neurons. Maybe we should make them like 1,000 neurons or something. Let's make it 2,000 something. Okay, 2,000 neurons, and then a ReLU layer. So because the fully connected layer is just a linear layer, if all you have is that linear layer, you have another linear layer. Linear and linear is not going to make. You're just going to get another linear function, right? A linear function acting on a linear function is just a linear function. So there is no benefit to having two linear layers right next to each other. But once you have a ReLU layer, which is an activation layer, right? You now get a non-linearity. This is now a non-linear layer. So you have a linear layer, a non-linear layer, a linear layer. This is a non-linear function. And then the classification layer, which just to make sure that we are solving a classification problem. Okay, so that's going to be our thing. And everything else remains exactly the same. I'm just going to run the whole thing, see what happens. So the training accuracy improved. The test accuracy improved a little bit, and then kind of pretty bad after that. Nothing much happens. The training accuracy remains. So we added an additional layer, but then the accuracy is horrible. Let's see if it does anything useful. It doesn't look like it's going anywhere, right? So the accuracy is just bouncing around 15% or something like that. So what's up with that? So this is kind of remarkably still a mystery why this happens, okay? We add this additional nonlinear layer, the performance is supposed to improve, but it just becomes much worse. And essentially, it has to do with the fact that this is a complicated optimization problem, and the optimizer is not able to find the optimum. It's just confused. It's searching somewhere, and it's not able to make progress towards the optimum. If it was able to find the optimum, almost by definition, the performance of this neural network will be dramatically better than this neural network, because this neural network is a subset in some sense of this neural network. This neural network contains this neural network and then plus has additional parameters to tune. So this neural network will, if optimized properly, will be able to do at least as well as this neural network and then better. But the optimization doesn't work for some reason, okay? Just because this is a complicated optimization problem. And then a few years ago, I'm just to comment this out, someone discovered that if you do some kind of a normalization step, so instead of adding just these two layers, just add a third layer called the batch normalization layer between the full layer and the ReLU layer. Um, let's do that. So just add that one extra layer, which basically normalizes the so if you have a particular mini batch, the mini batch gets pushed through this layer, and then you get to this layer. The mini batch has, I don't know, 100 different images. Um, you basically take the output for each of those images, take the mean of that of those outputs towards this layer, the standard deviation, and do some kind of normalization based on the mean and the standard deviation, and then pass that normalized version to the ReLU layer. That's what this layer does, roughly. It's called batch normalization because it's normalized based on the mini batch. In any case, some kind of a normalization. And then let's run that. That's the only additional thing that we did. And now um, the optimizer works pretty well. It sort of very quickly jumped to 90%, and it's now greater than 90% now. Let's let it run for like a couple of epochs, maybe, I don't know. And notice that, again, the blue is the training accuracy, and the black dotted line is the test data set accuracy. And the fact that they're following each other means that there's not much overfitting. At least the thing is doing as well on the training set as on the test set. It might either mean that you're not overfitting, or it might mean that the test set is not very different from the training set probabilistically. Um, so, okay, it looks like it's doing pretty well. It's still making some progress here. Maybe we'll stop it in a minute. You can try running it all the way to 20 epochs or whatever. I'm going to stop it in a second. I'm going to stop it. Okay. Okay, 97.24%, which is pretty good. Previously, we had 90%. By adding one more layer, we got 97.4. It looks like it might still improve a little bit. So if you let it run, like it's still doing an optimization calculation, it's improving things. Okay, so that's it. So neural network, adding the neural network gets an extra 7% on the uh, accuracy, I suppose, classification accuracy, and 97 point something percent, and maybe it's going to be 98 or something. Okay, so that's with these two layers. We can add one more layer. Or we can actually make this, instead of 100, we can make it 1,000 or 2,000. So we can make it wider, right? So what we did now is, so previously it was 100. So where your 784 is coming to 100 and then going to 10. So instead of 100, let's make it 1,000. That making a particular layer wider actually allows more flexibility. So let's actually see, maybe, I don't know, at the end of epoch 6.5 or something. Let's just run it for 6 epochs. Oops, not that. How long it takes compared to 97.24. It's not a perfect apples to apples comparison, but let's just see what that looks like. It's a bit slower, I think, because we made the network a bit bigger. Okay, maybe I'm not going to let it run all the way to 60 pops. So that's something that you want to do. Maybe I'll make this a homework problem where you try changing aspects of the network. May add more neurons, reduce the number of neurons, add more layers, etc. Okay, and see how these converged um, uh, neural performance depends on those kinds of parameters. Those kinds of parameters would be called architectural parameters because they affect or decide the architecture of the neural network. I'm just going to stop this now. Of course, running it only up to 60 epochs is not a fair comparison because this is a bigger network, so it may need to train for longer to get the same accuracy potentially. So ideally, you want to, again, we got 97.27% looks like without running up to 60 epochs. But in any case, um, ideally you want to run it to like sufficiently many so that it's still not making much progress. It's not making much progress anymore, and compare the two networks that way. Ideally, having more sort of a wider network should improve performance at least a little bit if the optimization algorithm is able to find the find the official, the correct minimum. Okay, so that's how you do neural networks on MATLAB. Pretty straightforward. Um, Now, instead of increasing the width of the additional layer that we added, we can actually add more layers in between. So um, here's something that's actually more like this, where you have two layers. Um, we have a fully connected layer that's a linear part, ReLU a nonlinear part, normalization, linear, batch normalization, ReLU, and then the softmax. Okay, so these 100, I just chose them randomly. Let me make them 300 or something. So anyway, let's run that. So even with the 100 and the single nonlinear layer, we already got something like 97 point something percent. So unclear if adding more layers will improve um, performance much. At least adding one more layer, it might. Still, we want to see that the blue curve is tracking the black dashed curve, suggesting that there's not a lot of overfitting. Looks like it may be doing better. Let's see. Maybe we'll end it at epoch 3 or something. Maybe epoch 4. Okay, so a little bit higher, 97.97 something. Um, yeah, you can sort of notice that if you, I don't know if you can zoom in here, but you can sort of notice that the blue curve is actually hugging close to the 100% mark, where it's actually, oh, there you go. It's actually going all the way to 100%. Okay, uh, or very, very close to 100%. So the function approximator is able to essentially um, classify every one of the training examples, 60,000 examples, exactly right. It's sufficiently complicated that it's able to do that. And then when you um, test it on the test set or the validation set, it's able to get almost 98% accuracy. Okay. Okay, so I suppose that's it for this video. On the next video slash videos, we will see perhaps how these other methods work, stochastic gradient descent with momentum. We will also see how to use a different class of neural networks called convolutional neural networks. Okay, so we'll stop that now.